Hi, my name is Ashleigh Henning. This is the Motion of a Falling Object Lab. The purpose of this lab is to observe the motion of an object that is falling from rest and falling very slowly. This was modeled with a sheet of paper that was dropped from rest as seen in this video. The system is the sheet of paper and the surroundings are everything else. The fundamental principles of this lab are utilizing the ideologies of Newton's second law, which relates the forces of the system, the mass, the velocity, and the time. However, in this model, there will be a non-zero net force on the system. This will include both the force of the weight, which is acting in the downward direction, as well as the drag force, which is acting in the opposite direction of velocity. The primary results of this lab have created an experimental and a computational model of the motion of the paper, as well as compare computationally a model with and without drag force. For both the computational model and the experimental model, the initial conditions were determined to have a position of 0.0932 meters in the y direction, a velocity of 0 meters per second in the y direction, as well as a mass of 0.02835 kilograms at time 0. This was determined with the calibration that was used by Tracker. The video experiment was analyzed using Tracker and this initial calibration. After using the systems to track position, it gave a graph to demonstrate the change of the y position on the paper. To determine the drag coefficient, knowing the initial position's velocity and a position at a different time, the final velocity was found. Then, utilizing Newton's second law, knowing that the F net was the sum of the drag forces of the total weight, then the drag force could be found to be 0.0207 newtons. Then this was used to be rearranged to find the coefficient of drag, which would be used later on in our computational model. This was a key component needed to build this model. Knowing that there were two forces acting on the object, weight and drag, these were added together to become the F net on the object. Then an iterative loop was run using Newton's second law, updating the velocity and position of the ball while updating the clock after each iteration. These points were then graphed and repeated while time was less than 1 second, incrementing every 0.01 seconds. This was the same loop used to determine when the force of the object was only the force of weight. The only difference is that the drag force was 0 on the object, and this led to a position and velocity graph that looked like this. The first significance between the computational model, with gravity being the only force acting on the object, and both the computational and experimental models that have both force and drag acting on the model, is that while force is only the force of the weight, the object is in free fall. This means that there's a constant acceleration acting on the system, and this is indicated by the linear graph of velocity. However, when drag is introduced, there is a non-constant force and thus a change in velocity. This means that the object is experiencing a change in velocity when there's the drag force until it reaches the terminal velocity. This leads to a non-linear linear velocity versus time graph as seen on the graph over here. The second difference is between the computational model and the experimental model that exemplify both drag and gravity, or the force of weight. The significant difference between these is coming from the likely sources of error. The paper is particularly susceptible to experiencing more than just two forces, especially from drafts in the room, causing the net force of the object to not be the one that is calculated. This is why, as you can see in the graph here, that these two do not align perfectly with one another. What does it mean with the drag force of the object? Drag force happens when the magnitude of the force of weight is equal to the magnitude of the force of drag, and these two forces are acting on the system in opposite directions. This means that when these have equal magnitude but opposite direction, the F net of the system is 0, and this can be seen graphically on this computational model. As it approaches over time, it will have a constant velocity, and this is the terminal velocity. What if the object was thrown initially? This would mean that the initial velocity of the object would be non-zero. However, drag and weight are still in the opposite directions of the model, and when in terms of terminal velocity, this would still exist at the same moment. It just would have the different initial conditions. Thank you so much for listening to our lab where we were able to observe Newton's second law, quantify and analyze drag force, and develop a computational and experimental model of our system.